Institute of Engineering and Technology.
Hello students. In the discussion of matrix algebra in Mathematics 1, now we are at the new part of applications which is known as eigenspace. Now in eigenspace actually we are finding two properties of matrices known as eigenvalues and eigenvectors. This is one of the most fundamental property of the matrix which is satisfied whenever we are considering the transformation using the matrix. Suppose you have a vector and if you are pre-multiplying it by a matrix, then it will give you a new answer. And that new vector is nothing but a vector which is resulting after transforming your original matrix, for which the matrix which you are taking in the pre-multiplication is the transformation. We know that matrix is nothing but the transformation tool to move from one space to another space. And if you are moving from one space to another space, you can move in form of the vectors. Suppose I multiply any vector which is 3 cross 1. I am taking a column vector of order 3 cross 1. If I multiply it by 3 cross 3 matrix, particularly pre-multiplication, it will again result into one new 3 cross 1 vector. This simply means that the new value is in a transformed space and the transformation is considered through the matrix of multiplication. Now once you are moving from 3D to 3D, the structure is different. How to find a direction in which the vectors are not changing their direction after transformation? Means they are only scaled. For example, if I ask you a question that you take a picture, you figure out the center point and you then draw a line x and y. And then what we are doing exactly in the mobile or in any application into the gadget, that is zooming in. If you zoom into the picture, what will happen? That center point remains exactly at the center point. The points which are on that x-axis and y-axis, they remain in the same direction, but they are changing their values. What happens to the another directions? The values are changing the direction and values are changing their location also. So this transformation is zooming, and that can be achieved by matrix. So interestingly, we can figure out before applying the matrix that which are the directions which will remain same, and in fact in that direction where they are remaining same, with which scaling factor they are going to be scaled. This is one of the most useful properties again of matrix algebra known as eigenvalue and eigenvector. So today in this talk I will give you technique to find eigenvalues of the matrix, techniques to find eigenvectors of the matrix also. So let us start this part of matrix algebra known as eigenvalues and eigenvectors. First of all, we are going to define it. So for given matrix A, and if there exists a non-zero vector capital X and a scalar value lambda such that Ax is equal to lambda x. This simply means that lambda is eigenvalue and x is corresponding eigenvector. Now from the definition itself, it is pretty much clear that A is the matrix pre-multiplied to x. Answer is again x multiplied with lambda. So that x is remaining same, it is not changing the directional components, but they are scaled by lambda. Okay, so the effect of this multiplication is remaining only in form of a scaling factor. The magnitudes of entries into these vectors are changing, the direction ultimately is remaining same. If this is happening, lambda is eigenvalue, x is eigenvector. How to find eigenvalues? So the method for eigenvalue is this. Take determinant of A minus lambda I equate it to 0, solve this determinant. It will give you one equation known as characteristic equation. Find roots of this equation. It will be known as eigenvalues. Collectively, we can form a set of all eigenvalues known as spectrum of the matrix. See, the spectrum of matrix is nothing but a set of all eigenvalues, means it gives you that with which magnitude those vectors in that direction or the direction of unchanged, they are scaled. How to find eigenvectors? Select one eigenvalue. Suppose I select lambda 1. Solve this system a minus lambda 1 I x equal to 0 and find that value of x. So it will give you direction in which the scaling factor is working. Go for another eigenvalue lambda 2. Again solve new system. Again you find x2. Similarly you can move up to lambda n. So remember, for any n cross n matrix, there exist n eigenvalues, correspondingly n eigenvectors. It may happen that some eigenvalues are repeated, some eigenvalues are non-repeated. So we need to perform this system of linear equation to find eigenvectors for distinct eigenvalues. At this junction, I want to tell you one thing. Number of times eigenvalue is repeated into the spectrum of A is known as algebraic multiplicity of eigenvalue, and number of vectors involved into the eigenvectors of eigenvalue is known as geometric multiplicity of eigenvalue. In detail, I will tell you through the example. So this is all about eigenvalues and eigenvectors. Combinedly, it is known as eigenspace of your matrix A. Let us consider one example. In this example, I will tell you how to find eigenvalues of the matrix, how to find eigenvectors. Suppose the given matrix is 1, 3, 6, minus 3, minus 5, minus 6, 3, 3, 4. It must be a square matrix to find eigenvalues and eigenvectors. So the first and the easiest step is to consider determinant of A minus lambda I equated to 0. Now how to take this A minus lambda I? Matrix A minus lambda times I. I is nothing but identity matrix of order 3. So lambda is multiplied to I. So it will convert that second part into lambda 0 0 0 lambda 0 0 0 lambda, and then take subtraction. So ultimately you are subtracting diagonal entries with lambda, and then take determinant, equate it to 0. Now at this junction you have two techniques. First technique is you just expand this determinant and then you find the equation. But the technique which I will suggest you to follow is this thing. You remember this formula, lambda cube minus s1 lambda square plus s2 lambda minus s3 equal to 0. Ultimately, it is a 3 cross 3 system. There are 3 lambdas in multiplication, so it will give you a cubic equation. This formula which I mentioned over here, highlighted into the bold letters, it will give you final simplified form directly. So it is comparatively easy. The only thing is we need to find S1, S2 and S3. So S1 is nothing but trace of the matrix. What do we mean by trace? Addition of all diagonal entries. Like here, A11 plus A22 plus A33, which is equal to 1 minus 5 plus 4 going to be 0. So that means S1 is 0. S2 is nothing but finding minors of diagonal entries. M11 plus M22 plus M33, these are minors. How to find minors? M11 means you select A11 and then delete that row, delete that column. So what remains? It will give you one submatrix, minus 5, 3, minus 6, 4. Same procedure you can apply for M22 and M33 also. And then expand this determinant. It will give you answer for first determinant is minus 2, second minus 14, third plus 4. Ultimately it is minus 12. And this means value of S2 is minus 12. Value of S3 is nothing but determinant of the matrix. You take the full matrix, find its determinant, answer would be 16. I'm not going into the detail of finding this determinant value. So now we have all three parameters, S1, S2 and S3. S1 is 0, S2 is minus 12, S3 is 16. Take input of this S1, S2, S3 into our main equation. So it will result into lambda cube minus 12 lambda minus 16 equal to 0. And this simply give you by factorization that first value of lambda is 4, second and third value are minus 2. And so the spectrum of my matrix is lambda 1 equal to 4, lambda 2 equal to minus 2, lambda 3 equal to minus 2. Coming to the next part, eigenvectors. As I told you, you will find eigenvectors by single value at a time. So we have two different categories of eigenvalues. One is 4, another is minus 2. At this point, spectrum of A contains lambda 1 equal to 4, lambda 1 equal to 4, it is coming only one time. So algebraic multiplicity of lambda 1 equal to 4 is 1. Minus 2 is appearing 2 times into the spectrum. So algebraic multiplicity for minus 2 is equal to 2. So there are two eigenvalues, 4 and minus 2, respectively with algebraic multiplicity 1 and 2. Is it clear how to find algebraic multiplicity? It is nothing but the number of repetitions for the eigenvalue. Now moving to the eigenvector. Select one eigenvalue which is 4. Take system A minus lambda I, x1 equal to 0. x1 is nothing but vector which we are finding, which is known as eigenvector. Now put value of lambda 1 equal to 4. So diagonally you subtract value of lambda 1. So it is 4. So I am taking minus 4 in subtraction with all diagonal entries, and then it gives me one system which is homogeneous system because all entries on the right hand side are 0. So there is no possibility of inconsistency, as one solution is always possible which is equal to origin. But now at this junction you can check directly whether this system is solvable or not directly. As we are finding direction, no need to solve it fully. By Cramer's rule you can always find the direction cosines of this solution, and for that what we can do, we can select any one row randomly in such a way that the determinant which is in the denominator of x, y, z must be non-zero for at least one value. So for that I am selecting first row. So I will take x upon something equal to minus y upon something equal to z upon something equal to t. I am assuming that there is one free variable. Okay, so now what will happen if I take this x value, then from that selected row is already deleted. First column is for x, second for y, third for z. If you are finding answer for x, hide the column of x. If you hide the column of x, the remaining portion will be minus 9, 3, minus 6, 0. If I want to find value of minus y in denominator, hide the column of y. So it is 3, 3, 6, 0. And for z, it is 3 minus 9, 6 minus 6. Solve this determinant in denominator and it will result into 18, minus 18 and 16. If I take this x upon 18 equal to t separately, it gives me x equal to 18t. If I take minus y upon minus 18 equal to t, it gives me y equal to 18t. And z upon 36 equal to t means z equal to 36t. So I can scale this value of t as it is free variable by 18t. So it gives me x equal to t, y equal to t, z equal to 2t. I am scaling this t with 18t. And then writing all values of x, y, z into a column form. It gives me in my first eigenvector x1 is t, t and 2t. Taking the t outside from the calculation, which is nothing but a scaling factor, it gives me a direction of eigenvector which is 1, 1, 2. If you join this value 1, 1, 2 with origin, it gives you a value of direction. It gives you a direction in which after transformation, your vectors are not changing the direction, but they are just scaled by factor 4. Now here, at the end of calculation of first eigenvalue, we received only one direction. So geometric multiplicity of 4 is 1. Algebraic multiplicity of 4 is also 1, as it is repeated only one time in the spectrum, and geometric multiplicity is 1 as there is only one direction at last in eigenvector. I hope it is clear now what do we mean by algebraic and geometric multiplicity. Now let us move to the second eigenvalue. Lambda 2 equal to minus 2. Lambda 2 and lambda 3 are same, so we need to go for only single calculation. If all three are separate, we need to repeat this process 3 times. So lambda 2 is minus 2. Take subtraction of minus 2, so ultimately addition into the diagonal entries. Now we received 3 rows. Now at this junction you cannot apply Cramer's rule. Why? Because if you select first row, second row or third row, you cannot find determinants in denominator to be non-zero. They all are going to be 0. The reason is all these 3 rows are same. So in that case, you just pick any one row, convert it into equation. I am selecting first row. So it is 3 minus 3y plus 3z, and answer is 0. Okay, and therefore in this answer, what will happen? We have one equation and 3 unknowns. So the degree of freedom itself is 2. That means we need to take 2 free variables. And as I suggested you, always select free variables from the last variable. So I will take z and y as free variables. Suppose I take z equal to t and y equal to s. So it gives me x minus y plus z equal to 0. So x is s minus t. So value of eigenvector x2 is s minus t, s and t. Now be very careful at this moment. We have 2 free variables into the single vector. So what I will do, I will separate this 2 s and t in such a way that one vector is corresponding to s, another vector is corresponding to t. So the first term s minus t, it contains both. So whenever I will write for s, the first vector is 1, 1, 0, because there is no value of t in the last case, plus t times minus 1, 0, 1. S and t both are free. Now look at this particular moment. We have 2 vectors at last in the solution. That means geometric multiplicity is 2. And algebraic multiplicity is also 2. Algebraic multiplicity is 2 because minus 2 is repeated 2 times into the spectrum. Geometric multiplicity is 2 because there are 2 different vectors into the set of eigenvectors. It may happen that algebraic multiplicity is 2 but geometric multiplicity is 1. It may happen. So I hope this is the solution for finding direction and scaling factor into the matrix. I hope all of you know now how to find eigenvalue and vector. It is most useful part of matrix. If you have any doubt or any difficulty into this, you just pause and ponder at any particular step, and you should follow the rules to find eigenvalue and eigenvector. The next talk would be on applications of eigenvalue and vector. We are going to derive inverse of the matrix using eigenvalue and vector. And after that, we'll also see one of the most useful property of eigenvalue and vector, which is diagonalization of the matrix. How to convert our matrix into the diagonal form. Once we have the diagonal form of the matrix, we know that determinant is easy, inverse is easy. In fact, finding rank, finding all normal forms or various properties of matrix will become easy. That we can achieve using eigenvalues and eigenvectors. One more application is there which is not actually in your curriculum, is known as PCA, Principal Component Analysis. This is in fact the most useful part of eigenvalue and vector from matrix algebra, which we are using currently in data science, AI and ML. If it will be possible, I will post a separate video on that principal component analysis also. Thank you.
Institute of Engineering and Technology.